pictures, you can look at it, the Earth from space, that people can tell you what day that is.
If you look at,
Katrina did.
Katrina Day, and this is...
you can see Katrina right there.
Yep, there she is. And it's right when she made landfall. And this is Tropical Storm Lee trying to organize out there in the Atlantic. So I like this picture because it really shows us, even with all our technology and feeling like we live a little bit separate from nature, we still are very vulnerable to weather and climate. Here's another view that shows you that humans have transformed the Earth over the last century, that we are capable of making changes on the planet that are significant. This is, of course, city lights from space. So another thing we're doing on the planet is changing the chemical composition of the atmosphere. This is a very famous curve, it's called the Mauna Loa curve. It's observations that started in 1958 at the top of the Mauna Loa Observatory in Hawaii. And Charles Keeling, also called the Keeling curve, is somebody who realized we really need to have good measurements of the concentration of carbon dioxide in the atmosphere. And he and Roger Revelle and a few other people really fought to get NOAA, National Oceanic and Atmospheric Administration, to set up this measurement. It's a very simple flask measurement done at Mauna Loa. The wiggles up and down are seasons. So the northern hemisphere has most of the land and most of the vegetation. And so when the plants are active in the northern hemisphere during northern hemisphere summer, it draws down the CO2 a little bit, and then it pops up during northern hemisphere winter. But you can see this increase, and we have, since 1958, since these direct measurements began, we have increased the CO2 concentration. Well, the CO2 concentration has increased by 25%, yes, sir.
This starts at 320, isn't that pretty high?
That's 1958, so the pre-industrial value is thought, which I'll show you, is thought to be 270 or 280 parts per million. These are parts per million by volume, yeah. But this is the direct measurement. So this will show, this is showing that the increase in atmospheric carbon dioxide is global. And this is a little bit longer scale. This is from the simple ice core from Antarctica. And when we dig an ice core, we don't have direct measurements, of course, going back to 1700, but we can get back by analyzing the bubbles trapped in the ice core. And so you see here, just as you mentioned, if you go back even farther in time, here's 2000, 1900, 1800, 1700, the pre-industrial value. The value of the CO2 is 280 parts per million by volume. This is also a pretty direct measurement. This is from the cores, and this is how we can reconstruct the carbon dioxide values as well as nitrous oxide and methane back hundreds of thousands of years before present. This is the present day. We're going back 600,000 years here, looking through ice cores of these bubbles. And here, I guess, this is methane. CO2 is the red one. And you're seeing here, there's an oscillation, there's variations, natural variations of CO2 through time, but then here are the current values going way up here, same for nitrous oxide and methane. Oh, I'm sorry.
I hesitated to interrupt.
No, that's fine.
So the current values are taken from ice core measurements as well?
So the ice cores, you can't resolve anything finer than a decade, maybe 10 or 20 years, because of the way the ice is packed in. So we have the direct measurements for recent. So you can see...
direct measurements in the atmosphere?
Yes, like for example, Mauna Loa and all over the world.
Do you intend to explain how we know a correlation between what we find in the ice to what was in the atmosphere several thousand years ago?
Sure,
Good.
I do.
I'm sorry.
Yes.
Do those peaks correlate to
They correlate with the ice ages.
Ice ages.
Ice
okay.
ages, yes. This is the Holocene, the last 1.2 million years, the Earth has been going through interglacial oscillations, mostly caused by variations in the 100% caused by variations in the solar radiation received at the Earth. So the Earth goes around the sun and has a certain tilt, it has certain features of its orbits. But because it's not a two-body problem, it's not just the Earth going around the sun, but there's also other planets perturbing the Earth's orbit, mostly Jupiter, which is huge. There's variations in all these, like the tilt of the Earth and the eccentricity of the elliptical orbit. And those change in regular ways on time scales of tens of thousands of years. And that's what leads to these ice ages.
So the last peaks, then are we coming out of the ice age, or present day?
Yeah, but present day, so yeah, they used to tell us here, we were in this, so this is kind of an interglacial in here. The interglacial periods are marked by higher CO2 levels, and we were in an interglacial period here. And so probably going a few more thousand years before we hit the next ice age. But instead, there's this anthropogenic perturbation. Yeah. Yes.
So Mauna Loa, for example, is what, 13,000 feet in the middle of the Pacific. So as long as you take readings at the same place, you're getting differences. But you get different readings at different, pressure is trying to equalize itself.
So CO2 is well mixed through the atmosphere. So the mixing time in the northern hemisphere, well mixed vertically as well as over the whole globe. The mixing time in the northern hemisphere, the winds are stronger in the east-west direction, so there's a fast mixing time of just a month or two in the northern hemisphere. And over just a few months, it's well mixed throughout the whole globe. And that's why the values taken, I thought I had a picture of that. But the values taken here, you can see, if you take values in a flask at the Antarctic, it'll look just like Mauna Loa, but without the little wiggle due to biological activity.
So you would get different figures at different altitudes.
Well mixed vertically as well.
Oh.
It's
So this
very
replicates
inert.
all over the world.
Mm-hmm. It's inert in the atmosphere. So it would be distinguished, for example, from methane, which is another greenhouse gas, but methane is very active in the atmosphere. It interacts with the soils and biological activity. So there's huge variations of methane over the globe, but not CO2. It's quite inert. It doesn't rain out. It doesn't do any chemical interactions. It's just well mixed over the globe.
Thank you.
Another question?
Oh, yes. Can I get to the one about, I just want to show you the bubbles in the ice. If someone was going to say, you're going to show us exactly how this is these little, and they're like, when the ice forms, it traps little bubbles, and it's just like taking samples of the air from hundreds of thousands of years ago, which is cool.
Is that a thin section of a core?
Yeah, these are the cores at the National Ice Core Lab. Here's what they look like. And they dig them. They have, the longest cores are more than 4 kilometers deep, and they're dug in the East Antarctic ice sheet, which is a very stable ice sheet that's been there for a very long time, so they can get a very deep core.
To what extent do we think that the greenhouse gases cause the interglacials, and to what extent do we think the interglacials cause the greenhouse gases?
The latter. So here you see this oscillation. CO2 is the most marked one. So the glacial interglacial oscillation is caused by variations in the Earth's orbital parameters. The eccentricity of the orbit of the ellipse, what's called the longitude of precession, or like if you're closest to the sun in the winter or the summer, and also the tilt of the Earth. And those can be plotted out, and we know exactly how they're changing. And that causes this. And so then when you have a time, for example, when it's a little bit warmer, because especially, well, it depends on which hemisphere, but if it's a little bit warmer, say, because the tilt of the axis is more or less or something like that, then the CO2 comes out of the ocean. Exactly as if you leave your Coke out, the CO2 bubbles out of it as your Coke warms, and that's what these are.
So all
This is not that. This is anthropogenic.
So all these interglacials that you have mapped back to 400, maybe 500,000?
Yeah, 600,
Uh,
even farther back now.
Those were all caused by orbital precession?
Yes. Yep. Yep. Astronomical theory of the Ice Age, or also called the Milankovitch theory. Yep. And you know, when we say theory, you know what we mean, like the theory of evolution.
I'm really tired of that.
So you can go to the astronomy department and ask them when the next ice age is?
Yeah. I
If there
mean, we
weren't
know what
people
the
on the
orbital
planet.
parameters are going to do. Are you in physics? It's a three-body. So there's a two-body gravitational problem that's very easy to solve. You add a third body, Jupiter, and you can see how the Earth's orbital parameters are perturbed. But there's three of them, so they add up in weird ways. It's not completely regular. Yeah? I keep blocking you, I'm sorry. Do you want to move it?
I can see.
You're okay, all right. Okay. So, we see that the CO2 concentration in the atmosphere is increasing, and I could show you methane and nitrous oxide as well. So what is the cause of this? And the cause of this increase is human activity. Let me show you how we know. Well, if we want to think about how much CO2 is in the atmosphere, we need to think about the cycling of carbon. When carbon is in the atmosphere, it's CO2. But when it's in limestone, it isn't, or when it's trapped in soils and vegetation, it's not CO2. But so carbon in the atmosphere is CO2, but we have to think about the whole carbon budget. And this is a little cartoon showing you the carbon budget and its perturbation by human activity. And these numbers are all, estimates from surveys and sampling and decades of work by many people. The red is showing the perturbation. So for example here's the air-sea exchange of CO2. CO2 is dissolved in the ocean, and it is also released to the atmosphere. And the unperturbed exchange is 90 gigatons, which is 10 to the 90 tons of carbon per year is in the unperturbed case. Right now, the ocean is taking up an additional 2 gigatons, an excess 2 gigatons of carbon per year, releasing 90. So the ocean is drawing down, helping draw down the CO2 concentration in the atmosphere. Our current releases, again, from inventories people take all around the world, is 9 gigatons per year. So of that 9 extra gigatons per year, 2 of it is getting pulled down into the ocean, 4 of it is staying in the atmosphere, and 3 of it is being taken up by photosynthesis, by vegetation, and also microbial action in soils and that kind of thing. So that's the overall of the carbon cycle, which again we have to think about if we want to understand that observed increase in CO2. Here is a plot of the total fossil carbon emissions. Here's 1800 to 1850, and then revving up. The black line is the total. The blue line is from petroleum, the green from coal, the red from natural gas, and this light blue one is cement production. So this increase in carbon emissions is going up in the same shape and the same kind of way as the CO2 increase in the atmosphere. So that's one piece of evidence that the CO2 that's in the atmosphere is due to this increase in fossil. I mean, we know we're putting carbon there. It's kind of circumstantial evidence. I feel very convincing, but circumstantial evidence. One thing I find even more, I threw these in, I thought you might be interested to know who's doing it. These are the top 4 emitters for 2013. India at 5.1%, Europe is blue. This is from 1960 to 2013, so Europe is actually having some success in emitting less. USA, here, we used to be #1, but now we're #2 since about 2006. But we're having some success in leveling off, maybe bringing down, and this is China.
Question.
Yes?
That chart and maybe the one before, how is that data collected?
From inventories, from people going to each country and looking at how many cars there are and how much gas is being sold and imported and all that. It's quite meticulous work. A lot of it's done through Oak Ridge National Lab here, the Carbon Dioxide Information Center in Tennessee. But yeah, global inventories, country by country, province by province, state by state. Yeah, and there's very good records of it, of course, for sales of all these things and
But
manufacturing.
it's car and plant emissions that they're looking at.
Yeah, but they can just look at how much oil was sold, right?
Oh, okay.
Yeah.
I'm not aware, I know China's economy is growing. I'm not aware that it's growing that much faster than India's. Is there some factor other than economic growth?
Well, I don't know, I'm not really an expert in that, but what I've heard of is cars have landed in China. Everybody's having cars now.
Don't forget they make all that stuff now. So all we've
So
done is
manufacturing.
exported what we used to make by making China make it in their factories instead. So
Yeah.
Well,
that
they also
possibly
do
they're
whatever they
replicating.
want to do. They don't answer any, put themselves.
They have bad pollution problems they're trying to get a hold of. Oops, am I going the wrong way? Okay, so I showed, I had a little digression where I said this is kind of circumstantial evidence because we know where we're putting the CO2 into the atmosphere. It's clear, and it's increased, and the CO2 is increasing in the atmosphere. But another piece of evidence that I think is really convincing is this one. This is showing, I don't know if you all remember about isotopes, but carbon has 12 protons, 12 electrons, but there's an isotopic form of it, which is carbon-13, which is heavier, excuse me, has more protons. And you can look at the ratio of carbon-13 to carbon-12. It's called the carbon-13 ratio. And we can measure this in the atmosphere and see that it's decreasing. There's less carbon-13 in the atmosphere with time. And the reason for that is that fossil fuels are light. They don't have carbon-13 in them. When plants take carbon from the atmosphere, they don't like carbon-13. They like the carbon-12, the regular carbon. They don't like the isotopic version. So we can tell that there's a plant source that's this extra carbon in the atmosphere, and that plant source is these fossil fuels, which of course jives with the increased burning as well. Is that clear? I'm not a good chemist. But this is the observed decrease in this carbon-13 in the atmosphere. Okay, so why does the climate care about this? Right, this is a trace gas in the atmosphere. Why is the climate sensitive to this change in the chemical composition? So this is an overview. I'm not going to go through the whole thing. I just did this with my class last week and they were stunned. But this is just showing you the flow of heat through the climate system. And this is estimates based on all our measurement systems, including all the satellites that are observing energy in and out of the system. This is the top of the atmosphere, and this is the surface. That's all I want to look at. At the top of the atmosphere, of course, the energy coming in is the energy from the sun. And that's shown here. Incoming solar radiation, 342, and the units are watts per meter squared. It's a rate at which energy is absorbed as is incident. Of that 342, 106 is just reflected away from the system. Clouds and ice at the surface, it never gets into the climate system. So just the difference, which is 236, comes into into the climate system. If we just look at the surface, you see that at the surface, 164 is absorbed by the surface. So this energy, this solar radiation is coming in. Some gets absorbed in the stratosphere, mostly the ultraviolet by ozone. Some is absorbed in the troposphere. Some it comes to the Earth in the direct beam of the sun. Some comes scattered to us, so it's what's called a diffuse beam, 164. So this is what's heating the surface, 164. The surface emits energy to cool itself. And it emits from the surface a whopping 387 watts per meter squared. Remember, it was only 164 over here, coming from the sun. And the Earth is emitting 387 watts per meter squared. And of that 387 watts per meter squared, 332 is turned right back down to the surface by the atmosphere. So the surface is cooling itself, but the greenhouse gases, primarily water vapor in the atmosphere, absorb that radiation, push it right back down to the surface. If we didn't have that going on in our atmosphere, it's the natural greenhouse effect. If we didn't have that going on in our atmosphere, the average temperature of the surface of the Earth would be -3 degrees Fahrenheit. Probably life would not have developed, we wouldn't have liquid water, we'd be looking pretty barren. But because we have this so-called back radiation from the atmosphere, that's the greenhouse effect, we have warmer conditions at the surface. The globally average surface temperature is 58 degrees Fahrenheit. So we have lots of liquid water and life could develop. So because this greenhouse effect is so important and powerful, that's why it matters if we mess with the carbon dioxide in the atmosphere, or the amount of greenhouse gases in the atmosphere. We're playing with this amount of energy that's pushed back down to the surface. And it's a lot currently, and it's important. And it's a really important part of the climate system.
I have a quick question.
Yes.
So you said 58 is the average surface temperature. I've heard 55 degrees for the average when you go down into the ground. Is that a new number, or am I confusing?
What do you mean when you go down into the ground? This would be the globally average surface air temperature.
Sure. Yeah, right at the surface of the Earth. So when you dig into the ground, the average temperature, the temperature is 55 degrees?
That depends on how deep down you go. It gets cooler, and then once you get really far down, it starts to get warmer.
Okay. I must have gotten something oversimplified then when I was
Yeah,
in
it
school.
depends on what level you are.
Okay,
But
so
just as a
another way to
reference.
ask that question is, has that number changed? Has this been a constant, wait, the 58, I mean?
Has it changed recently due to global warming, or has it changed in the past? It's definitely changed. Ice
Okay.
ages, remember?
Okay.
But the difference between an ice age climate and a non-ice age climate in terms of the globally average temperature is only about 10 degrees Fahrenheit. Which gives you some perspective when we start talking about global warming being 3, 4, 5 degrees. Yeah, so that globally average temperature, small change in that means a lot, yeah.
When you say the air surface temperature, you mean the entire planet, the oceans and the land?
Yes. Yeah, just kind of when people tell you, that the climate is going to warm by, I'm on the fly translating here between Kelvin and degrees Fahrenheit, but multiply by 1.8. But if people tell you, for example, that the globe is going to warm by 5 degrees Fahrenheit, what they're talking about is the globally average over day, average night, ocean, everywhere, globally average, annual average temperature of the surface air. The air, and usually it's at 2 meters. That's the number they're talking about.
So that temperature, our ability to cover the globe in terms of finding the temperature, we've increased in our ability to get that value, right? And
Yes.
so, are we using just, say, I don't know, direct measurements at different sites? Or are we using satellite technology to, say, measure infrared?
We're using everything that we can get. But a satellite will measure infrared radiation, as you say, this energy emitted from the surface, and it's characteristic. If you're up on it, the stuff what's going on tells you the relationship between temperature and emission. But the satellite only can, it
can
doesn't
tell you where
measure
it is.
temperature. And it doesn't measure temperature, it measures radiation.
Uh-huh.
And so you need to use an algorithm to translate that into temperature. And you need to know from what level, i.e. what temperature, what level that emission is coming from.
But we haven't had as many measurements for all the way, go back, say, 100 years. We had many fewer stations where we were measuring the temperature. So perhaps earlier values were maybe a little less reliable.
Yes, I think that's true. And there are, the way people handle that, it's kind of a job for the statistician people in the field. But what's usually done, and I think I have a figure that I'm going to show you of that, what's been done, so we've had thermometers at least back to early 1700s, 1705 or something, so there'll be a few measurements. And so what has been done is that 5 groups around the world have taken all the data that we've got and independently come up with a temperature change since, say, 1700. And they work independently, making all their individual decisions about how they're gonna do it. They also do something called a frozen grid analysis, where they'll only take, say, temperature measurements that we had in 1800, and just stick with those.
Apply
Don't
that
put
to
the new
now,
stuff in.
to the ones now. They will.
No, well,
Oh,
just stick with all the
okay.
old ones. Do a frozen grid analysis.
Okay.
They can freeze it, 1900 and then analyze it, 1950, or they can, do their statistical analyses about how to best incorporate all these. Then they get together, the 5 groups who haven't been talking to each other, and do it independently, and they put them all up next to each other. And so that gives you some kind of a range of what the temperature change would be if you made different decisions about your analysis. And I'll show you a picture of that coming along.
Maybe that's what I was going to ask. I was going to ask, what would that same chart, not that one, but the other one, with the radiation, what would that look like for the year 1814? In other words, has it changed
Which
much?
figure?
The one with the radiation numbers. Watts per square meter.
We don't know.
You're going backwards.
Oh.
Here we go.
So, what conclusions then can we draw?
I keep going
You're still
backwards no
going
matter what I do. It's a top and bottom issue, not a right and left issue. So this is the climatology. This is the current situation.
Can we assume it was roughly the same a couple hundred years ago?
Well, this is bigger because we've increased the greenhouse gas concentration. So what we know for example, if you double the CO2 concentration from the pre-industrial value, we've done it, but we've increased it to like 20% now, not 25%, or a little more than that, 35%, not 100. But we have really good radiation codes, and we can calculate that, for example, if you double the CO2, you increase this number by 4 watts per meter squared. So this number we think is bigger. We're only now having the observing systems to put this whole big global thing together.
In 1600 or so, the Thames froze all the way down to the ocean. And I don't remember what happened to Hudson Bay back then.
But you do remember what happened to the Thames.
All right. I imagine it was pretty cold.
He lived in England at the time.
So you could draw some conclusions about global temperatures from how cold it was in the little ice age, couldn't you?
conclusions about what
About the temperature, the average temperature of the Earth during
Sure.
the Little Ice Age.
Yes, most of the measurements would have been in Europe at that time, not really temperature measurements either. So in particular, the Little Ice Age is associated with something called the Maunder minimum, which is a minimum in sunspot activity. So sunspots you can see with your eyes. People have been observing sunspots through filters, I hope. But people have been observing sunspots for a very long time. Will you fix that?
Oh,
I told you I talk with my hands.
yeah, and when you're talking, you're poking the knobs, the buttons there. Okay, here we go.
So there's the sunspot cycle. This every 11 years. Actually, the full cycle is 22 years, and so every 11 years you'll have a high sunspot number of sunspots, and 11 years later a low sunspot, and back up, right? And when we have higher sunspots, it means there's more solar activity, and the sun releases more energy during those times, to the tune of about 1.5% of the increase in the solar radiation, solar energy coming in. And the Little Ice Age occurred during a very famous time when the solar, whatever nonlinear processes were going on in the sun at the time. It's a complicated hydrodynamic thing, but it went from, what was it, like 65 years with no sunspots. Low solar output, not the usual, get a kick, higher solar every couple of decades, you know. And in addition to that, there was some people think there might have been a lot of volcanic activity around the time also, but most people think it's mainly this Maunder minimum that's associated with the Little Ice Age. But the bigger question you're saying is, climate changes all the time. There's huge climate variability. How do we know this is just natural climate variability that we're observing? And the answer is that, yes, climate does vary all the time, but there's a reason for it, always, right? The laws of physics have to be obeyed, right? And so even if we don't know the cause, I can't think of an example right now, but like the Little Ice Age was the Maunder minimum, but there's got to be a cause for the change, right? So yes, the climate does vary. It varies quite a bit. That should make you more worried that it can vary so much. But there's always a cause. There has to be a cause for it. You know, you have to obey the first law of thermodynamics and Newton's laws and all that. So let's see if I can make this go forward.
Yeah, physics doesn't work in mysterious ways.
So what I was going to explain next was about climate feedbacks. So as I said, if we increase the CO2 concentration in the atmosphere, we increase more of the radiation coming back toward the surface, trapping the heat down near the surface. But still, CO2 is a trace gas. And so if you double the CO2 and nothing else happens, the climate system doesn't respond to that, you'll increase the globally average surface air temperature by about 4 degrees Fahrenheit due to doubling CO2. But what happens when you do that is you kick in these feedback systems. The climate starts responding. And there's two main things that happen, and they both amplify the effect due to a small increase in CO2. One is called the water vapor temperature feedback, and this is a loop, but this is just to remind me of it, but this will make perfect sense. If you increase the radiation back to the surface, you're going to warm up the surface, you're going to evaporate more water, right? More water vapor gets into the atmosphere. Water vapor is a powerful greenhouse gas. So this amplifies the initial change in CO2 by 3 to 4 times. The other thing that happens is called the iso-albedo temperature feedback. You increase CO2 a little bit, push more of this atmospheric radiation back to the surface, you're going to melt snow and ice. And of course, if you melt snow and ice, the surface is darker and it can absorb more solar radiation. So you decrease the brightness of the surface. And so these two feedbacks are the most powerful ones operating in the system. And they're both positive feedbacks, amplifying the initial relatively small temperature change due to increasing CO2 and amplifying it. And so you might guess that this means high latitudes. The ice albedo feedback means high latitudes warm more, for example, as we're observing. Okay, so that's the physics behind climate change, and I thought I would show you some of the observations. And this is showing you, this is 1,000 years ago to the present, and this is the atmospheric carbon dioxide. So you see this pre-industrial value of about 280 parts per million, and here is 200 years ago, 100 years ago, and the CO2 rising exponentially. And the blue is the temperature in Celsius, or degrees centigrade, and you see it also increasing, so with the CO2. Again, it's circumstantial evidence, but of course we understand the physics connecting these two.
And so there is
There they are. There's the bunch of them.
a lag. The temperature lags the CO2 concentrations a little.
So CO2 increased a little bit in here, but the climate isn't really sensitive to such a small increase. There's always, there's so much going on in the climate system. Volcanic activity, that kind of thing. And here, you see even effects of other processes in the climate system all the time. It's not just a single attempt, a hugely complex, nonlinear system.
Okay, again, a question about the source. So the measurements for CO2 in the atmosphere are now made directly in the atmosphere, is that right? And what year?
Since 1958, and then these earlier ones are going to be from the ice cores.
Okay.
And they overlap in here, so you can see they match up.
I had asked earlier how they get from the CO2 or the bubbles in the ice core to knowing what the the air temperature was in the atmosphere. Or, no, the CO2 in the atmosphere at that time. Say 10,000 years ago.
You have a bubble that's a little sample from that time, so they just
So they assume that there's the same amount in the atmosphere that is in the ice several thousand meters below.
Mhm. The ice is capturing the bubbles, it encloses it, and they can, of course, do this in a laboratory and look at the processes of encapsulating these ice bubbles. They're just little samples.
I've always wondered about that. I just didn't know if you could really
It's
assume
kind of
that that was
amazing.
what was in the atmosphere, was what was the same as maybe.
Yes.
Now I know.
Yeah, because the CO2 is inert. Methane isn't so inert, but there's no biological activity up there, so it just stays preserved, and it just is collecting these little samples for us.
Well, how are they getting the temperatures 1,000 years ago? Those are awfully
These-
fine ups and downs.
So a lot of these temperatures are from the oxygen isotope ratios. So these are isotopic ratios.
A guy named Harold Urey
O18.
developed this idea that you can use the O16, O18 ratios to get a temperature reading, and it turns out to be very accurate.
And the question about the data points that, when I've heard teachers talk about this, they talk about raw data versus something that's not been interpreted for everyone. Are these data points sort of directly from simple simple just mathematical addition, or are there some sort of interpretive things going on?
So let me go to the next one, because Steve had asked a very similar question. So this is global surface temperature as analyzed by 4 different groups operating independently, right? So there are decisions they have to make about how to do an interpolation or an extrapolation perhaps to a region where there were no measurements back in 1880 and this kind of thing, right? And these groups work independently, making each of these decisions. And then we throw it up and compare. And if you saw some going up and some going down and some staying the same, you'd go, this is depending on the individual analysis decisions. But that's not what we see. We see back in the day, back in the early part of the century, they've got some differences among them, and these would be due to different analysis methodologies. But all in all, it's low and it's going up, and they're in better and better agreement. I don't know what's going on there, but.
Yeah. Who, that's the Japanese one.
Japanese. Goddard couldn't do math back then, but they learned.
But even with that disagreement, I mean, you can see the general
I think it was a tsunami.
Where's the Hadley Center, please?
The Hadley Center is in Bracknell, UK.
Thank you.
Outside of Thank you, yeah. So this, you know, you have to analyze, it has to be analyzed. It can't be just one point. One point, if you look at, say there was a station that's been reporting, say, since, probably Paris has been reporting since thermometers were invented. But the problem is there's so much climate variability in weather, day to day to day. You have to put all of them together to look at the global temperatures, not regional temperatures. So there definitely is analysis and decisions that have to be made. And concern over that leads to this approach to having people do it independently, just make your own decisions about what you're going to do, and then let's compare.
Okay.
Yeah.
But then, over time, when they do get together and compare their data, do they not talk about their assumptions and then maybe come to a consensus about a better way to do it? No? They say, no, we're going to do it our way. And
Of course, they made the best, what they thought was the best decision.
Okay.
No, they may say, yeah, it might be equally good to do a different kind of analysis, but they all sat and did, maybe it was a coin toss on some, one group did one did the other, but yeah. I mean, you can imagine that this is a real big effort to put this together.
Question?
Oh, yeah.
So 0.2 in 1880 and negative 0.2 plus 0.5 in 2010.
And this is degrees C, sorry.
Yes.
Multiplied by 1.8 for Fahrenheit, almost
Okay,
double.
so we have a 0.7 of degree C change.
C, yeah,
in
almost
130 years.
Fahrenheit.
So what effects has this had on the weather, temperatures, the ocean levels?
I'm coming to that.
I'm anxious.
I appreciate the intro, yes.
Just before we get off that, there was a short time ago some controversy over this urban heat sink thing that was affecting some of these long-term temperature monitoring stations. Is that in any way related to the data that's being presented here? I know that was seized upon by
The urban
the
source.
fact that,
not the
yes,
sink.
sorry, it's not
Urban
sink,
heating,
urban heat
yeah.
source, yeah.
No, these are very carefully detrended for the growth of cities. So
Yeah.
in the US, for example, a lot of our reporting stations are in airports. Austin and what was it? They were at Miss Miller, the Mueller airport, and then it went out to ABIA, And in my group, we try to do climate projection for the Austin area. We actually work with the city of Austin, and we're always, they want to know how many more 100-degree days are going to be. That's what they're always asking us, right? And so we have to go back through these records. But when the airport moved from one place to another, it wasn't just that the city was encroaching, it's that you're sampling a different region.
Yeah.
North Austin could be 2 degrees cooler than South Austin on any given day. Yeah, but this is carefully detrended, that's one of the things they've taken into account here,
Yeah.
is if there was an urban heat encroachment here, yeah. And that's very, very small, the urban heat island thing. I mean, it's important if you're living in New York City. It gets extra hot there, but it's really a small area, so it's easy to take it out. Yeah.
Okay.
Okay. So these are the observations and to show you that temperatures rising more quickly at high latitudes, which we expect on the ice albedo feedback. This is high northern latitudes, the temperature trend from 1900 to 2000. Here's low latitudes, and here's southern latitudes. And I thought you might like to see the U.S. number. It was kind of interesting what was going on in the U.S. and we weren't really participating, lucky us, in the global warming regionally over the U.S. in this 1970 and 1980. There was actually over the central U.S. that there was this regional cooling. It was called the global warming hole over the U.S. Just, you know, natural variability, whatever, but I think we're catching up now.
Good. I'm rushing to the house.
And so we can explain the observed temperature increase without taking greenhouse gases into account. This is, let me walk you through this. The black line here is observations, that we were just looking at from 1880. This just goes to 2000. And this black line is the observations. The pink line, the red line, is model simulations in which the model is told about volcanoes, changes in the solar radiation coming in, it's told about greenhouse gases, and it's told about aerosols. These are sulfate aerosols. And we run the model out, this is the red line, and you can see that it follows the warming. The pink envelope is like an error bar around the model simulations. The models are not perfect. And so what we do is sort of like the people analyzing the temperature. We have a bunch of different models. There's 20 or 30 around the globe at this point, and we run all of them with the same kind of increases in CO2, and they all fall within this envelope. So that's like the uncertainty. But you see, they all go up, but you know, there's some range of uncertainty from the different models. If you go back and you run the model, this is the blue line, or the models, and you tell the model about volcanoes and about the sunspot cycle, the change in the solar radiation, this is what you get. Comes out here, not warming. And you can see that this model, the models are getting even most of, not all of these ups and downs in global temperature. It should give you some confidence in the models. They're, of course, based on the laws of physics. They're simultaneous solutions of 8 differential equations. And the time step taken is about, for this class of models, these global models, every 20 minutes. Because you have to do that to keep it that hydrodynamically stable and get unstable waves in it if you don't have that fine temperature. So these are huge efforts. This is what's pushing the development of computers in the world right now. These models are the biggest eaters of time and the biggest, they're really pushing for bigger and bigger computers. It used to be the nuclear codes, now it's climate models.
So question.
It's a good news, I guess.
So what we read from this is that there's about a 0.4 degrees C difference between natural and man-made. The man-made contribution is that much.
It would be just coming out flat if there were no sulfate aerosols plus greenhouse gases. And up here, yeah.
Yeah, the red is the anthropogenic plus the natural, and the blue is the natural.
And so it's about like what we saw, the 0.7,
Yeah.
right? About double it for degrees Fahrenheit. Sorry to translate this to Fahrenheit. I've got it somewhere because I have to show the city of Boston, but I have to show the city of Boston Fahrenheit.
Centigrade is fine.
Yeah. So, and we do look at other things in the system, of course. And one thing we look at is the ocean heat content. All of the heat capacity in the climate system is in the ocean. The ocean determines how quickly the heating can proceed. And so we look at ocean heat content, and we see that increasing. We can't, of course, go back to 1880, but back to the 1960s or so, we started getting some depth measurements in the ocean. So these are increases in the ocean heat content. This is, I guess, another view of the increasing ocean heat, global ocean heat content.
I have a question on a previous slide.
Yes.
What determined using 700 meters as a band to look at as
So the ocean is usually described as having 3 layers. The ocean mix layer is the top ocean bubble, and then there's something called the thermocline or the pycnocline where water temperature starts decreasing quickly. And the top section of the ocean is the one that interacts most vigorously with the atmosphere. And that would inspire
And that's the
that
700.
That's kind of deep for the ocean mix layer, but I'm assuming that's why they made that.
They wanted to make sure they
selection.
got all of it, I guess.
I guess.
Okay.
Yes?
Well, I have another ocean question, but it goes back many slides. You showed the carbon uptake of the ocean being +2 something.
Gigatons, 10 to the 9th tons of carbon per year.
And the oceans are getting more carbon acid based. Is there a point at which that uptake will stop due to the acid content?
More due to the temperature. If the temperature warms up, it'll start giving up some of that carbon or taking in less of it. The concern with acidification, well, so there's a temperature effect, right? When the temperature warms, the ocean can hold less dissolved CO2. The biological effect, there's something called the ocean biological pump. And in the surface areas of the ocean, the reason for that extra 2 gigatons of carbon that the ocean can take up is because it takes in that CO2 and it pumps it into the deep ocean. It takes it away from the surface layer, which allows the ocean to take in more. And the way it pumps it away from the surface, again, the ocean biological pump, is that plants and animals make use of this carbon that's in the ocean, for example, to make shells of shellfish, or it gets into plants, and animals, when they defecate, it settles under gravity into the deep ocean. So it's a removal of carbon from the upper ocean. And it's called the detritus rain. But it's very important for keeping, so the ocean takes some extra CO2 from the atmosphere and then puts it into the deep ocean through this biological activity. And so a concern would be if the ocean gets too acidified, it might decrease the amount of life going on in the ocean and weaken the biological pump. But that's probably out 100 to 200 years.
So of that 2 gigatons, how much of that would be photosynthesis, like for zooxanthellae or other kinds of aquatic photosynthetic?
I don't know how that's broken down to plants and animals even. Ocean heat content. And here is sea level, measurements of sea level. Of course, as we melt ice that was sequestered on land, it goes into the ocean and it raises sea level. And the other thing that happens is when you warm anything, of course, it expands. And so there's 2 components to increasing sea level. One is increased melt from water that had been sequestered on land, and the other is the expansion of the ocean. And the increased sea level is about half each of those effects. Half expansion, half additional water.
What's the measurement? 60 what?
Oh, sorry.
Millimeter.
millimeters per year, about 3 millimeters per year currently. This is a very hard measurement to do too, apparently. You have to do it near the coast, and each coast is different, and you know, the shape matters and everything. But what helps a lot is being able to do this from space. This is these TOPEX, Poseidon satellites. We can actually measure the elevation of the surface within a fraction of a millimeter now from space. So that's helped see the overall rise. But that's why this is only going back to 1993.
And that's radar?
Yeah, I think so, or LiDAR maybe. This is a plot of glaciers. I guess you're old. This is the mass of the glacier, and this is, they just translated this into what it means, the contribution to sea level. But you can just look here, these are glacier masses, and this is just coming from 1960 to 2000, and these are the European glaciers, like the Alps or the blue one. And they were doing okay for a while, maybe coming down now. Here's the Andes, the Arctic in gold, the Asian mountain glaciers in black. This poor thing is Patagonia, the southern tip of South America. And these are the North American glaciers in the 2 shades of green. And if you're more of a visual person than a map person, here's people have been vacationing at glaciers for many years, and there's lots of pictures. So here's Glacier National Park in 1911 and 2000. This is the Corrientes Glacier, which is in the Andes from 1978 in July and July 2004 on the same exact point. See the rocks are the same. And glaciers and ice in general is very interesting because it doesn't change day to day, right? It kind of integrates a climate system, and this is why we're looking a lot at the ice sheets. Because it doesn't really respond to weather, it doesn't go up and down quickly, but integrates a climate change signal over decades. Here's a nice picture of Kilimanjaro. It's 80% gone now. And a point I like to make is, these glaciers are actually water sources for a lot of people. And in addition to impacting people and ecosystems, we're losing important information about past climate with these mountain glaciers disappearing. These are annual rings in a mountain glacier, just like a tree would have rings. And people, the paleoclimate people love these things to study past climate, to learn about how climate changes. I just have some pictures to show you about the Arctic. Here's, how am I doing on time?
I don't even know what time it is, but we don't have
Just
any.
leave it. Oh, is that okay?
Yeah.
I'll take you through a few of these pictures.
Yeah, if you don't want to stay, you can leave anytime you want. Some of us are going to stay and watch.
So this is the Arctic sea ice, and this is during the summer in the northern hemisphere. The black line is the average for the sea ice from 1981 to 2010. And then a few individual years are on here, in particular the last 5 years, and they're all down here, below the average. And we had a really stunning melt back in 2012. People were worried it was going to go even lower, but it's come back a little bit. But the Northwest Passage opens that year. This is, again, visually what it looked like, 1979, and then what 2003 looks like. And the Northwest Passage actually opened up in 2012. There's the Northern Sea Route, the Northwest Passage. The Northwest Passage is where Roald Amundsen went through, and this passage, not this one, opened up in in 2012. And of course, oil companies are all what they're drilling now because it's melting.
When did Amundsen do his exploring?
I don't know what year that was.
Well, a decade.
That was the first trip to the North
It
Pole.
was in the early part of the 20th century.
10, 11, 12,
Roughly
10 to 12.
1910 or 20, something like that. Yeah, he was the first person to the North Pole. And he actually got back alive. Good job. This is the Northwest Passage opening up in 2012. And the Antarctic is not melting yet. In fact, the Antarctic and the Arctic are very different. The Arctic is covered by water, and the Antarctic is covered by this big continent. And they're behaving very differently. And in fact, this is the same figure for the southern hemisphere, for the Antarctic sea ice. Here's the average, the black line. And you can see in the last 5 years, we've actually got record high values of sea ice around Antarctica. And what's happening there is, it's a little bit complicated to explain, but essentially the winds are increasing. The westerly winds are increasing around Antarctica due to the warming at low latitudes, and it's causing more upwelling of cold water and actually getting a little bit cooler. And the climate models actually predicted this, well, some of them predicted this a few years ago. And Greenland, I'll throw in a little, oh, I'm sorry.
So you said in the Antarctic, it's bringing cold water from the ocean? From
Yes,
the deep
there's
ocean?
more upwelling, it's
So-
stronger upwelling driven by stronger winds.
So does that mean is the average temperature of the ocean around Antarctica going up, or? Because of that?
Not where it's upwelling, the deep water.
Right.
So the warming isn't into the deep water,
Okay.
right? So it's bringing water at 3 Kelvin or 2, I don't know if I can do Fahrenheit on that, but yeah, bringing cold water up from the bottom, about 3 or 4 Celsius. So very cold water at the bottom. And the global warming doesn't get down to, 4 or 5 kilometers.
Well, I just wonder if cold water is coming up, then something has to replace it. And I was wondering if it was averaging out higher.
Yeah, there's a big global circulation of water called the thermohaline circulation. It's driven by density, which is controlled by temperature and salinity. Yeah, but that whole circulation has time scales of 2,000 years. So if there's more water coming up, the place where it goes down, or one important place where it goes down, is in the North Atlantic, right? So you might say, oh, there's more coming up in Antarctica, and maybe the sinking is bigger in the North Atlantic. But it'll take, hundreds of years before we see that.
Okay.
It's just a big, slow system. Greenland, I love this picture, and just because you mentioned it, I'll just go to this picture. This is showing the change in the ice cap. This will help you maybe for your next one. Greenland is melting. The blue areas is melting, decrease in the ice cap height around the edges, but it's getting taller in the middle. There's more snow falling on it because of the change in the winds and the storm tracks. So some people pointed to this and say, the skeptics, Antarctica is actually getting taller. It sure is, but it's melting around the edges. And if you look at, this is just melt rates in different years for Greenland. So anyway, thank you. This is somebody put up, I love this. It was in DC. This is the snowmen protesting global warming. It's a lot of work. It's a little bunny rabbit.
It's not there anymore because it melted.
It melted. But I thank you so much for your attention.
Any more questions? I think we're asking so many questions along the way.
So, people in the scientists in the scientific community, they figured this out for quite some time. So how do you do this knowledge in your daily life or politically? I think the hard thing about being an environmentalist or feeling like you want to be an environmentalist in the U.S. is that you get so much conflicting information. And you don't know what to believe. Like, for instance, I'll give a really specific example, like whether to buy a Prius. You have a whole slew of people that will tell you, oh, but the batteries are very, very detrimental to the environment to produce, and they don't last very long, and So, people in the know, in the scientific community,
I
what do
just
they
know about
they-
the climate, I don't know anything about Priuses.
Well, I'm not asking you for our recommendation, I'm just wondering, how do you all get information on how, like, what does this make you want to do with this information, yourself personally? And how do you get information that isn't, inaccurate and politically based?
Well, I'm a scientist, so I just get data and I know the physics. I've been studying it for many years. I don't there's no information coming to me that is politicized, right, as a scientist. What I do personally is I come out here on a Monday night and talk to you all, and, I do that quite a bit. I also, in my teaching, when I was hired here, I just had to teach one graduate course a year, a semester. My teaching load is one course a semester, and I switched, so I alternate my graduate courses in the spring, and I teach an undergraduate course called Global Warming. And the first year I taught it, there were 30 students, and this is the third year I've taught it, I have 90. It's growing every year, and it's wonderful. Students who really get it and understand the issues. I hope they go and talk to other people. And it's only about the science, it's nothing about politics or anything, just this kind of stuff, yeah. And you said that the scientists have known about this for a while. So I wanted to tell you that the first paper that said that if we're burning all this coal and fossil fuels, we're going to increase the CO2 in the atmosphere, and that's a concern for climate. The first paper on that was in 1870. This is no surprise to anyone in my community. And if you understand anything about how the climate system works and know how important that radiation is from the atmosphere, there's just no question about it.
Right.
So, but it's just been, of course, very politicized. And
Right.
it really disturbed me for many years, and I just had to just do what I can do. And I also console myself with, I look at statistics about it's something like 50% of the people in the country are creationists, right? Don't really go with evolution. So what chances climate change?
Console yourself?
We just do the best we can, and we try to vote, and we try to educate people, but it's kind of an education issue.
Can I ask a question that's kind of related, but maybe it'll be like a 7th grade question, but that's where I'm at. Okay, so everything's cooking and getting hotter, but we're headed toward an ice age. What's the problem?
So it's an issue of timescales. So the glacial interglacial oscillation happens on timescales of 20,000, 30,000 years, up to 100,000 years. And this global warming thing we're doing is on the scale of 20 years, not 20,000 years. So it's an issue of the timescales involved. So the next ice age, for example, yes, might be coming, but it'll be coming in 20,000 years. But we're warming the climate out, and we're, some people even argue that we may not go into another ice age if the CO2 levels are so high.
So
It's a time scale issue, decadal versus tens of thousands of years.
So let's say the methane in the Arctic tundra gets released, causes the ocean conveyor to stop. That's the hypothesis. Triggers an early ice age. Is that?
Did you see the day after tomorrow?
No.
They had the ice coming into New York.
Oh.
So the ocean conveyor, this is that sinking of water in the North Atlantic, and it pulls, it's the Gulf Stream feeds into it. And so the Gulf Stream is what warms the east coast of the US and also across to England, for example. And so if that sinking stopped, the Gulf Stream would be weakened and we would have regional cooling. But it wouldn't affect Asia, for example.
I was thinking, maybe the scenario I was thinking of is runoff from the tundra in cold water. Icebergs don't come down south as much anymore. The cold water, they're changing the salinity, stopping the conveyor from, not from the Gulf, but maybe
Right,
from.
freshwater influx.
Yeah.
So we have an example of that from the end of the last ice age. So in the last ice age, the glaciers came down into Pennsylvania. If you've ever been across I-80 in Pennsylvania, that's actually built on the moraine, the stuff that was dumped in the end of the last ice age. And it started melting back from the south to the north. And as it melted, the meltwater was going down the Mississippi because the St. Lawrence Seaway was frozen in. At some point, it got far enough north, and the whole diversion of this turned to the North Atlantic. And all of that fresh water flowed into the North Atlantic. And that weakened the thermohaline circulation, the sinking there by about 20%. It didn't stop it, right?
Okay.
But it is one thing people look at and worry about. You know, there's a lot of worry about that because we worry a lot about abrupt climate change, things that can happen quickly, because it's very hard to adapt to something that happens quickly. I've even done studies on shutdown of the North Atlantic. It's called the North Atlantic Deepwater Formation. It's not slowing down yet. There's a huge monitoring system out there, and that would be a more long-term thing. But if it leads to cooling, it's because we don't have the Gulf Stream coming up, and it would be a regional effect of cooling.
Okay.
It would be the next ice age.
Okay.
Sir, I read this book by this guy that sounded really smart.
Yeah. He's a geologist.
I think it's called Deep Future or something like that. And
Deep something.
so he's explaining all of these systems, all these
Yes.
systems which say that the warming that people are predicting over the next 100 years will actually be over the next thousands of years. Do you have an opinion on that?
No. But we're already seeing, the warming now on this decadal time scale. So I don't have an opinion. I have, the evidence from the observations and from the physics-based models that say,
Well, his models are based on if all human activity stopped dead right now, it would continue to warm for thousands of years.
Oh, that's true. Yeah, we're already, I wouldn't say thousands, I would say 200 years, something like that. So the residence time for a CO2 molecule in the atmosphere is about 100 years. So even if we were to stop right now, we're committed to a certain level of climate change. And the CO2 will stay up there and keep doing the feedbacks, and we'll get the back radiation. Yeah, I don't know if it would be thousands of years. I would think it would draw down pretty substantially after a couple of hundred because of the residence time of CO2. And methane, of course, is a much shorter residence time. Sorry.
So how much do your models say the temperatures will increase over the next 10 years and over the next 50 years?
So mid-century is one time we looked at.
Mid-century
More
would
like
be
40
what?
years, 2050.
2050?
Is that 2050, 2050. So we look at mid-century and end of the century, so I can rough from that. So and I caveat this by saying it matters how much the emissions are. It matters a lot how much the emissions are. So a big uncertainty is what are the emissions going to be like in 2100?
I'll interrupt your answer by saying I see a lot of sources that say there's a threshold, we're almost there. If we get to that threshold, we're all doomed.
Tipping points.
Is there a tipping point?
There is not a tipping point globally, but there may be regional for certain regional climates.
Okay.
One example being the North Atlantic, if you shut off the. But so for the warming in this globally average surface air temperature, 2050, a number of 3 degrees C.
3 degrees C above today?
Above pre-industrial, of which we're about halfway there.
Wait, 3 degrees.
The warming
above.
due to increasing CO2 above pre-industrial levels of mid-century around 3 degrees C, which is like 4.5.
And we're halfway there, so 1.5 more degrees.
What about 2100?
And then, yeah, 2100.
And then 2100, I see numbers more than double that, so something like 5, 6 more, because it's exponential. That's the problem.
More than today.
Then 2050,
5 or 6
additional.
more.
That's when we get to trouble in the second half of the century. It's our grandchildren, or bigger trouble. But no, reverse.
But we can turn it around, you said, if we fix the issue.
And so this would be for what I think is going to happen, which would be called a business as usual scenario. I'm sorry to be jaded, but I don't think we're going to do
Well,
it.
politicians make the decisions, not the
Right.
scientists.
Well,
Well, the
burn off.
voters at some point hopefully can.
Well, not in
Yeah.
China, voters don't make it.
And one might say it's the industries, the companies that are making the decisions.
Yes,
Yeah.
that's the way it works.
It is. So that's, my numbers are for business as usual scenarios. Now, there are methodologies being developed to, sequester, what they call, pull out the CO2, and, that may be a technological help.
Bigger trees.
Bigger trees, more trees. But what they're doing is I just read in the New York Times yesterday, there's this new cement plant coming online where they're taking the CO2, cement production produces a lot of CO2, especially Portland cement, and they're taking the CO2 produced and they're drying it off to make other, like bicarbonate soda and stuff like that.
I think cap and trade is a good idea to help control.
I think it's the
Does it
only
have to?
thing, it's the only thing that will happen. You have to put a tax on carbon.
Worldwide.
Yeah.
It's the only thing that would ever work. Yeah,
The notion of reducing the heat coming in by putting, say, an aerosol of sulfuric
really
acid
against the aerosol
seems crazy to me.
Yes.
Because, Venus tried that.
The thing that scares me is when we mess around with stuff we don't have complete knowledge about.
Yeah.
And the other thing that people have talked about doing is iron fertilizing the southern oceans,
Oh, yeah.
because the phytoplankton their growth is limited by their anemic. They don't have enough iron. And so they've actually done little trials of this and gone and dumped iron filings in the southern oceans to try to bring it up.
And the waters in the Pacific around, with people with nice clear blue water, because they do have such they have enough iron that keeps the waters clear, right? And so what they did was they're looking at putting it in places where they're kind of murky, I guess.
It's, they were looking at the southern oceans, at 60 degrees south, the ocean goes all the way around.
Oh, yeah, I see.
No, apparently it wouldn't bother anybody there, right? But
Oh,
I'm kind of against, geoengineering it's called, and it's really getting a lot more play now. And it really scares me because I kind of know what we don't know about the system, and I know that we have surprised, the ozone hole was a surprise, for example. It
there's
wasn't predicted.
the law of
It just
unintended
worries me.
consequences.
I'd rather see our efforts being put to draw down. Yeah.
In your business as usual models, does burning natural gas have any effect versus burning?
I don't know what the details of those are. So the whole process, I don't know if you've heard of the Intergovernmental Panel on Climate Change. It's this whole global process that goes on about every 7 years where everybody contributes. The first thing that happens with that is all the economists and population people, experts from all different countries get together and put together these scenarios for the future. And those scenarios then are given to climate scientists like me as something to force our models with, to put into our models. So, this is really high-level economics modeling that's done, that I don't know exactly what the assumptions are.
Okay.
Well, the IPC has been working strongly in mitigation more than remediation. What to do as the climate and the temperature increases, how to mitigate the effects of that by getting different crops and stuff like that. Now that's where their focus has been the last few years.
Well, I think that there was a chapter in the last IPCC report on remediation as well. So they have different working groups, like I'm a member of working group 1, which is the physical basis for the, and then they have all the people working on adaptation and mitigation. Then they have group 1, you know, and the energy side of it, for which drawdowns would go, as well as solar, wind, and that kind of stuff. Did you?
Yeah, somebody mentioned, just because you brought up Venus earlier, and I've read that Venus is never going back, like it will always be stuck at 700 degrees.
It's a runaway greenhouse effect.
Has everyone ever modeled Venus to
Oh,
be
yeah.
like, when did it pass that point of no return?
I think
You know?
Venus was always
Oh,
like
man.
that. Mars probably changed. Mars looks like it lost an atmosphere, but Venus is close to the sun. So what happened on the Earth is, if you remember back to that carbon budget, I didn't really point it out, but there's huge amounts of carbon in the limestone and in the rock. And Venus, and if that carbon was released from all that limestone and rock, would be Venus. But Venus was hotter, closer to the sun, and it didn't get this solid rock formation. And so all the carbon is in the atmosphere in Venus. Yeah.
So how long will it take to terraform Mars?
So, yeah. So, you know, when I teach my class, I have this great, you should have this guy come talk. He's an astronomy professor at Southwestern, and he comes to give people perspective. Are we going to use up this planet and go to another one? You know? And the answer is no, it's not, it ain't going to happen, you know. Even an Earth-like planet, you just can't get there. The energy it takes and the, you know, and the time and this kind of thing. And the students also say, well, they give up on Venus right away, but of course they always think about Mars. And so I'm remembering his answer to this question just 2 weeks ago. And one of the ways to do it is to, there's a microbial solution that you can do to put in microbes and try to reconstruct the atmosphere there. And that takes thousands of years to do that. And the other way to do it is try, so there's a lot of water underground in permafrost on Mars. And people think about trying to get that water into the atmosphere to increase the greenhouse effect and maybe start this positive feedback. And he had some calculation of what kind of energy that would take. And it was like a ridiculous amount of energy.
And it doesn't get
So
as
there
much
can be
sunlight.
domes is the, you know, some kind of dome life, I guess.
Or underground on Mars.
Yeah. He makes this point, you know, he says, you know, Lewis and Clark came and they went from the East Coast to the West Coast, you know, and what did they have to explore? They had water all around them, they had all their food running around there, they had air, they had Sacagawea, you know, and they barely made it back alive, right? Think about if you go out to another planet, you know, it's taking you, like, what have you got? You've got nothing, maybe a hydrogen molecule here, you know. You have nothing, and so these calculations on could you make it, could you bring everything with you, are failing. Yeah, big distances.
Well, that's assuming we send oxygen breathing carbon-based.
Like us.
Right. You know, and when I tell my students that, I say silicon creatures are possible, and I refer them to Star Trek. You know, for the silicon creatures, they just look at me like, what is this old lady talking about? You know, Star Trek, what's that? None of them remember the silicon monsters.
Well, thanks again.
Yeah.